So welcome everyone. Can you see my slides still?
Yes.
Thank you. So welcome to the 11th Impact Workshop. So this is actually truly 10 years of impact this year. Actually would be in a couple of months. So Arvin and I are very happy to be there and to have organized this event. So we realized it was organized a bit late or pretty late. So we are particularly thankful to the program committee members who were able to do the work in a pretty short amount of time. And obviously we are very thankful to all the people who submitted papers and attend the workshop today. So I don't want to waste your time. So we have a great program packed into two sessions. The objective was to help people attend wherever they are on Earth, except if you are in Australia, where it's really bad. If you are in Eastern Asia, it's also inconvenient, but I think Tomo managed to attend at least the first session. So please stay as long as you can, and we'll have an exciting side channel for communications as well. So we have Gather Space that was set up thanks to a recommendation from Vincent. So thank you, Vincent. So you'll find the URL on the webpage. Just be mindful that we have a quota of up to 50 simultaneous participants. So if you think that the space is crowded, which is not the case now, please leave the room if you're not using it. So you can get used to it and play with it until 8 p.m. tonight if you want to chat, have a virtual drink or whatever. Yeah, so
is there a link? Excuse me.
Yeah,
is there a link for the Zoom meeting somewhere?
I just
no, on the HiPEAC website only. Zoom meeting.
And to be clear, the link to the Gather site is also in an email?
No, no, that's on the webpage. This
okay, perfect.
Is on the webpage.
Okay, thanks.
Yeah. So I'd just like to thank the program committee members again, and let go with the first presentation. So the first paper, the first paper will be Polygeist and will be presented by Regé from Imperial College. This is joint work with colleagues from MIT, Google, and TUE. So I think you can share your slides and get started. And please be mindful of the time as well. So we have 20 minutes for presentations. We have some buffer for discussions, up to 10 minutes, depending on how much intensity there is in the discussion. So Q&A is a very important time, and especially in these online conferences. So please don't overshoot your presentation time.
Sure. By the way, I cannot share my screen at the moment. It might need to.
Can you please try again?
Yeah.
Yeah. Should be okay. Okay. So, can you all see it at the moment?
Yes.
Okay. Great. Hi, I am Rachel. I'm from Imperial College London, and I'm very glad to be here to present our paper Polygeist, and from a fine C to MLR. And this paper is co-authored by Billy, Lorenzo, me, and Alex. We are kind of motivated to do this paper from the following perspectives. First, compiler people are now kind of looking at MLR, and MLR provides us a very versatile representation. So we can use them to represent polyhedral models, and that could be beneficial. And second, there are decades of polyhedral research actually, and there are many excellent tools are built. And I know many of you are the authors of them, but we haven't been able to reuse them in MLR at the moment. So basically, we cannot pass MLR code to these tools and get the result back. And third, we know that Polybench is one of the benchmarks that people currently use to evaluate their polyhedral optimization. But they are in C. So to justify our verdicts on benefits from doing polyhedral MLR, we might need to represent properly MLR first, so that we can get a read of the kind of unexpected effects and do fair comparison. So there's one note that we are not focusing on using polyhedral tools to speed up MLR. That is, we more concerned with how to provide a fair baseline for future subsequent work. So Polyguys is a platform to establish baselines for polyhedral representation, polyhedral transformations within MLR. So it has the following 4 different modules. First, we have a front end that can generate MLR code from C or C++. And we have a module that raises this standard MLR dialects for polyhedral transformation by raising them. And we have also embedded some of the existing polyhedral tools into MLR so that we can just use them, apply them on the MLR polyhedral representations. And also we evaluate our performance with the polyhedral benchmarks, which is Polybench. And finally, you have an end-to-end evaluation on standard polyhedral benchmarks. So here we have a bit of background on what is MLR. We can see it as a toolkit for representing and transforming code. So it basically provides us a modular and extensible representation via the concept of dialects. So as you can see on the right-hand side, it's a ecosystem of MLR, and there's quite a lot of dialects in them, and there are transformations between them. And also, MLR is not opinionated, which means you can choose the level of abstraction that you might want. And instead, it kind of integrates the state-of-the-art SSA-based compiler technologies. So you can easily reuse some of the excellent passes that others developed based on the state-of-the-art researches. And at the bottom of this page, I attached a generic form of the MLR code, so you can get a hint of what MLR is. And there's one specific dialect we are looking at, which is called affine. It basically represents static control paths with polyhedral friendly loops and conditions. So this one example matrix multiplication is shown on the right-hand side, and you can see it looks very much like our instincts, and it has the following concepts, the core representations. We have symbols which represent parameters, and have dimensions that's more or less the induction variables of loops, and we have maps, which are basically maps from symbols and dimensions into other dimensions. And we also have sets which are integer tuples constrained by a conjunction. So you can use it to represent integer sets, which are pretty helpful for polyhedral optimization. So the first part of Polygas is the front end. It basically, as I said before, is transforms from C code to MLR code. Well, we don't directly go into a defined dialect first. We go to a lower level. It's called SCF. This dialect, it represents static control flow without the affine constraints as the affine dialect requires. So lowering from C code to SCF is straightforward. We can directly lower the C control flow, like for if, directly into the SCF counterparts, like for and if. And we can represent variables and array by MLR memref, which is a construct for memory reference. So, so here I show the example of how the front end lowering works. Left-hand side is a sample C code, which basically sets a value of an array with a calculated address. And if we directly lower them into, translate them into MLR SCF, we get the code on the right-hand side, which looks pretty scary, But if we look at the highlighted parts, we may find out that it basically translates what the C code is. You allocate the memory for the variables and store some initial value into it, and you do the SCF for loop, which basically load the value of the loop index variable, multiply it by 2, and store the given value into that address. So it looks pretty straightforward, but that doesn't look like polyhedral or look as simple as what a polyhedral model should be. So what's the most important is we don't have the affine constraint on them. So we need to do some raising work, which basically raise from SCF dialect into affine. We do the following 3 things. First, we try to eliminate local variables by a newly designed, a customized MLR mem2reg, which is transformed from memref to registers. We use this path to eliminate local variables, if possible. And also, we try to raise load and store, which used to be in the standard dialect. They don't have any constraints on the affine address. We try to raise them into affine loads and stores if possible, and which is basically possible if we can detect that the given address calculation is an affine expression. And we also do some progressively index folding to reduce the lines of code. And we try to change the if statements if their conditions can be raised. So basically, these 3 conditions for the raising. And here we show what the raising result could be. So from the left-hand side, it's a pretty long SCF MLR code. And on the right-hand side, we kind of extract the core part of it and turn them into a single affine for with a single affine store. And we can see how we calculate the address and fold them into the single line of affine store. So the next part is, since now we have the ML affine code from C code, we are going to optimize them using the polyhedral methodology. And but the problem is, for now, it is pretty difficult to leverage existing like well-used polyhedral tools. So our approach is we first try to convert ML affine code into OpenScope, which is the interchangeable format among many polyhedral tools, and it's very familiar to many of you in the community. And so the problem is, how could we translate between the MLR code and OpenScope? So we need to transform from MLR to OpenScope first and do the polyhedral optimization, and then transform them back to MLR. So that's what's the second part of PolyGuys looking at. So the first challenge is the OpenScope expects polyhedral statements in the C-like style. So basically we can, so like this line, it shows the core part of a matrix multiplication. But MLR is at a lower level, and we cannot exactly relate one store instruction about how it computes the stored operands. So, or in another word, one OpenScope statement may correspond to n MLR operations. So what we do is we devise a simple algorithm here. So first of all, we extract to match one select statement, we extract one memory write operation, and we traverse its SSA use-step chains. And until we find out all the operations we're meeting are loads or symbols. And in that case, we can terminate. Right-hand side shows one example that how we extract the corresponding MLR code for the matrix multiplication into one function call. And the arrows are the use-step chains. There are 2 different problems we might need to deal with for this algorithm. The first is region spanning. So one use-step chain may span multiple regions, which is basically the chain can cross 2 different loops. So, but if we still follow that chain, we might end up with a statement that is ambiguous to schedule initially. And it is also very difficult to construct it back to MLR once we do the polyhedral optimization in the external tools. So what we do here is we insert a scratchpad for each use step across regions. And the second problem is read after write hazard. So the problem is there could be many polyhedral statements that use the same affine load. Well, that affine load, the address that affine load loads from might be overwritten by another store operations in other statements. So there could be read after write hazard in this case. So what we do here is we first detect this problem using a simplified value analysis, which is a bit conservative, but we can improve that later on. And given if we find such hazard, we insert scratchpad to decouple the dependency on the same affine load, such that we can schedule this schedule the different polyhedral statements without this read after write hazard. And once we solve all these problems, it's like pre-processing the MLR code. We can try to outline the statement into kind of like its external functions. So so there are some things we need, some details we need to deal with, like if there are some local variables or local symbol definitions, we need to lift them to the main function, such that these symbols can be detected and analyzed in the open scope format and by the polyhedral tools. So so overall, the translate to open scope is it has the following 3 steps. First, we pre-process the MLR fine code by the previously mentioned passes. And next, we for each extracted polyhedral statement, we get its 3 very important relations. One is its domain, which are constraints on the statement's iteration space. And we need to get its initial schedule, which can be easily derived by the operation order and the nesting of regions. And finally, we can get the access relations from the affine load and store operations inside the extracted functions. And we also store symbols for the future ML code regeneration. So here's one example that I gathered that translates MLR into the open scope representation. So so once we optimize open scope, the current approach which we use is we try to obtain the Klug AST, which can be reused to generate MLR code. So the Klug algorithm is quite stable and is very excellent to use, and we want to get the most of the advantages from them. So we regenerate ML code simply by traversing the AST that Klug generates, and it should be very straightforward. And there are some symbols that we previously stored in OpenScope. We can transform them back to MLR values and operations. So this is overall pipeline. After polyguys raise the fine, we do some pre-processing, translate OpenScope, and use Pluto to optimize the OpenScope and transform the OpenScope back to MLR affine. And finally, we lower it into the exactable format in LLVM. So, so next I'll show how we evaluate polyguys. We do it in 2 folds. First, we evaluate the performance of polyguys front end with Clown. And then we try to find out is there any difference between polyhedral optimization results with the native Pluto. So here are the results we have got for the comparison with Clown. All these benchmarks are gathered from Polybench, and we can see that the most of the results are they're giving very similar performance. And for those that are a little bit higher than what we expect, we have the following explanation for them. First, we solved some difference already by dealing with the ML module generation and also the LLVM layout translation to solve some of the differences. And those are already removed from the benchmarking results. And there are still some remaining gaps that we are trying to resolve. They're like memory allocation function and strength reduction problem. And due to the difference in induction variable types, MLR use index, which is similar to 64-bit integer versus a 32-bit integer that is currently used in Polybench. This difference should be solved in the future. And to compare Polygas with Pluto, we also run the same Polybench samples, and there are like still most of the results give similar results, similar performance, but there's still some gaps. And there's one major gap, major reason for the gaps is we need a finer tuned Klug AST generation control. So given the same configuration and the same schedule, we pass them to Pluto by CLI2 and using the libpluto's API, we can get very different Klug AST. So we're currently still looking into it, and hopefully we can get some insight from them into that problem later. And there's some other issues like induction variable types and some auto-vectorizations that might be triggered for Pluto, but not for Polygast. So you can find more details in our paper. So here are the conclusion of our work. So Polygast, our project provides a tool for fair comparison between ML-based polyhedral flows with prior existing polyhedral tools. We have a C++ front end, we have integrated polyhedral tools, and we have an end-to-end comparison. Polygast, hopefully, it enables future research on polyhedral MLR transformations. And for the end-to-end comparison, we have found like 1.25% difference between the Polygast front end and Clown, and we have a difference of in average by around 7% between Pluto and Polygast optimized code. So here's some acknowledgements. Thanks to all the collaborators. And we are happy to take any questions you have. Thank you.
Thank you very much, and thank you for keeping the time. So that was a great talk. So we have one question already on the Q&A from Sven. Since you can speak, the best would be to ask it live.
Okay, so can you go back to slide 4?
Yeah, sure. Right, yeah.
Maybe I misremember. I thought you mentioned somewhere that using this framework, you can give access to MLR to polyhedral tools, but apparently it's not on this slide.
Oh, access to polyhedral tools.
Oh yeah, okay, slide 3 was, I guess.
Yeah, okay.
At least I read it in the paper. So my question is, how could they do that, since apparently the communication is purely through open scope?
Yeah.
How could then still get access to these transformations or analysis in MLIR?
Sorry, so your question is, how could we access to the transformations within the external polyhedral tools, like Pluto or LSL?
Yeah, I thought you mentioned that was one of the advantages of this approach.
Oh, yes. So our approach is, as you mentioned, we first transform MLR code into the equivalent open scope representation. And we pass the open scope representation to the existing polyhedral tools. Like in Pluto, we can just run a single API that transforms the open scope representation of the polyhedral model into an optimized one. And after that, we can transform the open scope representation back into the MLR by first generating the Klug AST, and then map the Klug AST's expressions to the equivalent MLR affine expressions. So that's how this. So if there's any polyhedral optimization that can be used within the external tools, we will do that on the open scope we get.
Yeah, if I can complement, because I'm also on this paper, OpenScope has this sort of extensible list of extensions, as these are actually called, in which you can put any information that you want in any format that is somehow parsable. So we can communicate extra information through that extension mechanism. It does not give you API interfacing between polyhedral tools and MLR analysis. So you cannot just say alias analysis dot has alias into MLIR. Will need some deeper connection, but at least there is a technical possibility of connecting through the open scope extension mechanism.
Okay.
Thank you.
So there is a related question by Ari on the Q&A. So combining MLIR with polyhedral tools seems to be particularly interesting when not starting from a C program. So basically, Ari, would like your comments on this, and also is asking whether when starting from a C program, would it not be better to actually first use polyhedral tools to convert it into MLIR directly?
Okay, thank you for the question. I think so. For the first part, yes, it is indeed interesting if we don't start from the C program, and it is also very doable in Polygeist, because we can just pass the ML affine code into the polyhedral tools interface we have developed, and it also gives us some additional flexibility to control what kind of statements we want the polyhedral tools to recognize and optimize on. And this might resolve some of the problem we have seen in the existing C-based input code. And for the second one, we haven't tried that yet. So
I can complement it as well.
Yeah.
It's a bit of a mean answer, but I don't see a point of first doing polyhedral transformations on C, generating C, and then going to MLIR for no other reason than using MLIR to compile C. So MLIR is not a C compiler. There's no C compiler. Actually, this work starts to build C compiler for MLIR, but there is very little benefit we can get by taking pre-optimized C input and pushing it through MLIR.
I understood the question as we could just go from C directly to OpenScope as opposed to MLIR, and then since C and OpenScope are more alike.
I
think that's how I interpret the suggestion.
Yeah, it's more like, why do you actually even need MLIR here? And I think that this project is twofold. That one is we want to be able to call into polyhedral tools from MLIR, whatever the input. So we can come from, say, TensorFlow, convert it to affine loops, call Pluto or ICL scheduler, get back to MLIR, and do the regular stuff, plug into TensorFlow. And once we have it, how do we compare this thing? Because if you want to compare this TensorFlow matrix multiplication to affine polyhedral optimized back to affine MLIR, how do I compare it to polybench gem? It's not a fair apples to apples comparison. I'm comparing polybench's implementation of gem plus Pluto plus Clang versus TensorFlow's implementation of gem plus MLIR plus something else. There's too many factors. So that's why we need this input from C to basically be able to compare to other tools that start from C. But we don't need to start from C to use Polygeist.
One other thing that I'll just add on to Alex's explanation as well here is the fact that C also doesn't necessarily have the best representation for certain types of constructs. For instance, it doesn't have a naive sort of like vector type or equivalent of operations within it, whereas you can have a nice representation of that within MLIR, and similar with a couple of index calculations and the like, that, well, I also do concur with Alex that the bigger advantage of using Polygeist is being able to sort of like separately compare and separately integrate all of the different polyhedral components into one sort of like end-to-end workflow. So you can swap out, you know, either the source code or the particular transformations. There is the potential for a little bit of an advantage of having something that's slightly more IR based than something more C based. And we do see that directly with a couple of things that we have to do, namely for ternary operations that are used to represent selects inside of MLI are slightly nicer to work with.
Thank you. So let's take one last question. Actually, okay, two more questions. So Benoit, you want to ask a question live?
Oh yeah, sure. So actually, slide 3 is really good for my question. I see this approach as a AST based raising and lowering based on Clang and LLVM. But what what strikes me is that the closest element of comparison should be perhaps naively poly, which is just a CFG plus SSA alternative to raising and lowering. So I was wondering if you guys had a chance to make comparisons with directly with poly.
Yeah, I think I'm going to take this question. So thank you for that. We have compared, we have run some experiments on poly, and we're trying to get the result. But the key thing for now is poly uses its own SL. Well, it doesn't use the original Pluto algorithm. So, but we use Pluto, and we cannot make an apple-to-apple comparison for now. There are some. So once we can change the internal polyhedral optimizer to what poly uses, we would do the final apple comparison then.
Okay.
Okay, thank you.
And the last questions ask for a quick answer. So Cedric Bastoul is asking, can we choose not to pack several MLIR instructions to C-like statements? Those the unpacked form allow optimization, and what is the impact on completion time?
Oh, that's a very good question. So so for now, because we want to match with the open scope as well as what the Pluto expects, which is a C-like statement. We haven't tried to. We're like motivated to pack the statements for now, but there could be some possibilities that we can enable more optimizations by not packing them. Yeah, and especially one thing we're going to try is for those very long or very complicated C statements, we're going to split them into multiple statements at the MLR level, and transform it into a different open scope such that it might enable more optimizations from the polyhedral tools.
Thank you. So I think I will invite you to continue any discussions on the Gather space during the break. And I created a table at the south side of the room on Gather if you want to discuss open scope in particular. And so thank you, Ray. And if you can please stop sharing so that Sven can share his slides. Thank you. So the next presentation will be given by Sven Verdoleher. It will be about a templated C++ interface for ISL and its joint work with other colleagues from Cerebras and with Google.
Thank you. This presentation is about a templated C++ interface that we developed. I'll first go through some motivation of why we need this templated interface and then discuss the interface itself. So I'll start with a general description of Polyhedral Compilation. As you know, it's analyzing and transforming programs using a polyhedral model. And this polyhedral model is some kind of abstract representation of a program, which is instance-based. So it looks at statement instances and array elements, not statements and arrays as a whole. And it's using some kind of compact representation possibly involving polyhedra. But that's not the main point. The main point is that we have these different parts in the presentation. So these are typical parts that Polyhedral Model would contain, which is the instance set, the set of all statement instances, the access relation, which maps statement instances to array elements that are accessed by the statement instances, and dependencies that map statement instances to other statement instances, and also a schedule that maps statements instances to some kind of order on the instances. So here's a small example of matrix multiplication. The instances of this program are over there, and the accesses are over here. So as you can see, we can have either sets containing these tuples here living in different statements. So these are instances of statement S1, and over here we have instances of statement S2. And similar things happens for the access relations, and a schedule could look like this. Now, the main point is that we have to deal with different kinds of objects. So as shown on the previous slide, we can describe statement instances, we can describe array elements, we can describe connections between them, so the accesses. We can also have binary relations on statements. So for example, dependencies. We can also have a mapping from statements to some kind of ordering or to processors. And we can also have more complicated relations. For example, if you want to define a mapping from array elements to memory elements, that will typically depend on the statement instance. I mean, you won't necessarily map a single array element to a single memory element, but it might depend on the statement instance, which means we can't just have a mapping from array elements to memory elements, but instead we have a mapping from a pair of statement instances and array elements to the memory element. And you can create all kinds of different relations like this. So besides these, there's many more. Now, if you're then writing a Polyhedral compiler and you have to deal with many different kinds of these polyhedral objects, then you often wonder, so here's a function and it takes something, but what exactly is it? Or if you have an operation on two of these objects, does it really make sense? And the standard answer in a statically typed language like C++ is, well, we look at the type. But as I'll show in the next slides, the types don't really help in this case. So if we look at a library like polylib, every set is represented by a polyhedron. And there's no special representation for binary relations, but usually when you're forced to use them in polylib, you would also represent them in a polyhedron. So at compile time, there's no differentiation between these different kinds of sets and relations that we actually need to deal with. And even at runtime, polylib can only check the dimensionality of the object. So if you're giving these two objects, who knows if it makes sense to combine the two. And if you look at omega, it's very similar. So everything there is represented by a relation. Again, no differentiation at compile time. At runtime, omega does make a difference between sets and binary relations. So if you give it these two inputs, it would know it couldn't combine them with each other. So then look at ISL. I'll describe the plain C++ interface, but it's very similar to the C interface. So ISL does make a distinction between sets and binary relations. So at compile time, at least this difference is available. But that's it. So making a difference between dependence relations and access relations is also something that's not available at the type system level. Now, at runtime, ISL can make a further differentiation by not just looking at the dimensionality, so the tuple size, but also at tuple names. So that's these things. If you try to combine this access relation with this set of instances, then ISL would be able to tell you that's not possible, because this is dealing with instances of S1 and this is dealing with instances of S2. But if you then use these union objects, so union sets or union map, they can actually contain elements with different tuple sizes and tuple names. So for example, this was an access relation from either S1 or S2. This is combined in the same object. So if you would try to intersect the domain of this thing with any kind of set, you wouldn't be able to tell if this is the right kind of object that you're taking intersection with. Another important thing to notice here that is, even though this object contains elements with different tuple size and tuple names, it's still mapping statement instances to array elements. And it's this kind of property, or this kind of the meaning that we would like to express in the type system. So that's what I'll describe next. So the main goal is to be able to differentiate between different kinds of sets and relations. So making a difference between an access relation and a dependence relation, for example. So if you have a function that accepts one of these and you try to pass it something else, then you would hope that the compiler would tell you about this, and so that you know there's a problem. Also, if you're, for example, trying to intersect the range of an access relation with a set of statement instances, again, you would want the compiler to tell you about this, because you could only intersect the domain of this relation with statement instances. So we want to be able to do this at compile time. It should also be application specific. So ISL shouldn't have to know about all the different kinds of applications and all the different kinds of relationships that it needs to deal with. So ISL should only provide a general framework, and then the application will define the concrete types. It should also be compatible with the plain C++ interface. This is to help people who want to translate from the plain interface to the templated interface. And then finally, it should be as easy to use as possible. And the main focus here is that at some points you will have to express that you're dealing with a relation from, say, statement instances to array elements, but you don't want to have to repeat that all the time. So at the signature of your function, obviously you want to specify this, but in the body of your function, you don't want to have to go on and keep repeating this same type information. So the basic idea is pretty simple. For each plain type in the plain interface, you introduce a template type in the templated interface. We decided here to give them the same name, which means we have to put them in a different namespace. So obviously, if you move your code from the plain interface to the templated interface, you will have to make some changes. And then for each type, so it's not actually every type in ISL. So I only mentioned sets and maps in this presentation, but there's several other kind of types in ISL. It's only the types that involve some kind of tuple, so sets and binary relations, for example, that get a template type. And essentially, we add a template parameter for every tuple in the object. So a set can have a single tuple. That's the most common use. For example, here you could define a type st, which might mean statements, and then you could define a set that has statement instances by using this template argument. But besides sets with one tuple, you can also define sets with no tuples, and those are used to define constraints on the constant symbols. So for sets, we have these two different specializations, one with 0 template arguments and one with 1 template argument. And then for a binary relation, obviously, you would have 2 template parameters. And here's another example of a map from statement instances to array elements, for example. and that would be an access relation. So a bit more information about that. The template types are derived from the plain types, so that you could use a template type where a plain type is expected. But obviously, the constructor is made private such that it won't work the other way around. So if something is expecting a template type with a specific template argument, then you don't want the compiler to just figure out what it should be and then do it for you. You have to specify it explicitly in that case. That's exactly the kind of checks that we want to have. And then I'll show you an example. So here we have a function taking an access relation, and then we're trying to call another function that's also taking an access relation, and a third function that's actually taking perhaps a dependence relation, so a relation between statements and other statement instances. And then we want the compiler to complain about that, and it does. And actually, Clang gives very nice error messages here. So it not only figures out that you're passing in the wrong type, it will also tell you exactly where the problem is. So here it says you have a union map mapping something, whatever it is, to array elements, and you actually need something that maps to statement instances. And so the same thing that we did to types also applies to methods. For every plain method, you introduce a template method. And the shared template parameters, they express that the tuple kind needs to be the same. So let's look at a couple of methods defined in this way. Let's take, for example, intersect domain. So this is defined within a map from some domains to some range. And then you can see that the argument that you need to pass is a set that is in that has the same domain as the domain of the binary relation. And conversely, for intersect range, here the template argument needs to match the second one of the binary relation. And then the resulting type will in this case be the same, but obviously that can also be different. For example, the apply range method, if you pass it, so what it does is essentially it has forms some kind of composition of binary relations. So if you have a binary relation from a domain A to domain B, then you would apply something from a domain B to domain C, and the result would be something from A to C. And this is exactly what is reflected in this template interface. So you expect a second binary relation that starts from the target of the first one and then has some other further target, and then the result goes from the original domain to the final target. And this is not a template argument, parameter specific to this method. But if you specify a concrete argument, the compiler will figure out all the template arguments, of course, assuming it's the right one. If you pass in the wrong one, it will also tell you about that. So here's another example of that. It's very similar to the type 1, but here we're looking at applying this operation where we have an access relation and a set of indices. It's possible to intersect the domain with those instances, but it's not possible to intersect the range with those instances. And this is exactly what the error message tells you here. Again, you passing something in the statement domain, and it's expecting something in the array domain. Now, it's not quite as simple as that. There's also more complicated types of relations. For example, this storage map that was mentioned a couple of slides ago, so where you map a pair of statement instances and array elements to memory elements. And there's different kinds of operations that you could apply to this kind of relation, but one of them is to extract a mapping from just the statement instances to the memory elements, so projecting out the array elements. And this is a method that is provided in the plain interface. But you can't just add this to the original specialization of map, because it only has domain and range. And with this information, you can't describe what the result should look like. So this method is not available in this specialization, but another specialization is introduced with, in this case, 3 template parameters. And in the domain, you see that it's further split up into a nested domain and a range. And then in the method, the results can reference this nested domain so that it has the right type, which you couldn't do in this specialization. So I think most of these have been covered. It's just ease of use. There's some more that needs to be said about that. Specifically, there are some methods that are make it more cumbersome to use. And these are methods that create objects from one type from objects from another type. For example, this universe method, it takes a description of a tuple, so just the size and the name, and this is specified by an ICEL space in ICEL, and it creates a universe set. Now, if you just take this method, and because the only argument is something from another type, it could only be represented by a static method. And if you want to use that, then you have to not only type the entire type, but also all the template arguments. And in this case, it's pretty simple. But if you have these nested types and stuff, then it can get pretty complicated, and you would prefer to avoid that. So what we did is that we introduced a new name for the same method, but one that is applied to a space and then returns a set, instead of being a method in set taking a space. And so it's called a universe set, because now it's the method name that needs to specify what the results should be. And if you then need to use it, you can just apply it without bothering specifying any of these template arguments. Now, there is one case where you do need to specify template arguments, and this is, for example, the set range tuple method. What this does, it replaces the identifier of the range of a map. And since you change the name, you change the meaning, which means that you potentially also change the kind of tuple. So you would have to have a different template argument. And so that means you have to specify it explicitly. And what it looks like is this. So here you see there's another template parameter, but in this case, there's no way to match it using any of the template, any of the method arguments. So that means that whenever you use this method, you explicitly need to mention this second argument. So you need to specify what kind of tuple this is when you assign it a different name. I'll skip this because it's not that important. So there's 2 implementations of this concept. One was within tensor comprehensions, which was presented at HiPEAC last year, and another within DTG, which was presented at Impact last year. And hopefully this will be available soon. And there's 2 things that you need to take care of when you try to go from the plain interface to the template interface, is that you should exploit type deduction and declare your variables as auto. Otherwise, you have to change the type all over the place. And another thing is that it turns out that quite often the same variable gets used to store different kinds of data. because in the plain interface, it may just be a set, and then you could use this set variable to store different kinds of sets. But if you add the extra typing information, then it may turn out that there are actually different kinds of sets, and then you should use different variables to store these results. Okay, so we introduced this templated interface, and it allows you to get compile time checks using these fine-grained user control types, and it should be available soon.
Thank you very much, Sven. So we have a few questions already. So I'll start with Sanjay's question on the chat. Unless you want to ask the question right away, Sanjay, but I think it's pretty clear. So is it possible to actually implement like more advanced type checking with like richer type theories, like array bound checks in this kind of approach?
I'm thinking. I
the
guess.
Question is, maybe, yeah, sorry, go ahead.
Yeah, I think it would be possible. I never thought of that. That wasn't my main concern. Not my main motivation for doing this kind of thing. Yeah, it could be considered, yes.
Could be considered, and maybe there are use cases from like pedagogical purposes. Maybe when teaching ISL, that could be useful. I can think of this. So we can go back to that later. And the other question is from Vincent on the chat, on the Q&A. So more comment than a question, but feel free to comment. From my point of view, a library for integer sets should be generic in the sense that it should let you do any kind of random stuff. I'm paraphrasing. Including wrong stuff. So don't you agree? And Sanjay has an opinion.
Well, if you want to do that, you can just use the plain interface.
So that's, yeah, I guess that, I don't know if Vincent, you want to speak, maybe. Aravind, can you give the mic to Vincent? Maybe he wants to elaborate.
Yeah, I can do that.
I mean, I can see where it's coming from, but we better from.
Vincent, I have given you permission.
Yeah, okay, thank you. Well, nothing specific to add. It was just my idea that a library should be as generic as possible. So I think that this restricts the use of a library.
Well, it doesn't need to. It's the application that defines the types. If it only wants to have one type, if everything is the same, it could do that. Even using the templated interface. But for those people like me who want some more control, you can have more refined types and then enjoy that.
So I have
okay, thank you.
Sorry, go ahead. Okay, yeah, so that was, yeah, one question is, so what happens when you want to do slightly wrong things, like converting arrays into statements, for example? I don't know, maybe you're generating new forms of statements with new arrays, and for some reason it's better just to start with an array set, and then you want to make it a statement set. How do you do that?
That's exactly what this function would, what this method helps with. So if you have something that originally was statement instances and you rename them with the intention of having them in arrays, this is exactly the kind of method that you would use.
Okay, good. And my second question is, what about schedule trees?
So schedule trees don't have tuple information. As the tree itself, of course, what's inside the tree does, but that's not covered yet.
Do you think it would be applicable?
So in in DHC, we don't use schedule trees yet. That's why I haven't looked at it yet.
Okay, any more questions? So Sanjay, you can resolve the question on the Q&A. I think.
No, it doesn't give me permission to type anything in the Q&A box for some reason. So that's why I've been commenting in the chat box.
Okay, but don't you have a button to say done or something?
I have a button to say done. Oh, okay.
Yeah, great. Thank you. So we have a log of the questions.
So we have retired questions. Thank you.
Retired questions, exactly. Okay, so thank you very much, Sven. You can close the sharing of your slides. And so the third talk in this session will be given by Patrice Quinton from INS Rennes. It's joint work with Tomofumi Yuki from INRIA Rennes, and will be about representing non-affine parallel algorithms by means of recursive polyhedral equations. We cannot hear you, Patrice, but we can see the slides.
You're muted.
Yeah, you're muted. Bottom left.
Momentarily, you were not muted, but we still couldn't hear you.
It's the icon on the bottom left. Yeah. I don't know if Arvin, you can unmute him also.
Let me try.
That's okay.
Yeah,
Sorry.
We can hear you.
So I'm going to present some work about how to represent non-affine parallel algorithms by means of recursive polyhedral equations. So, okay, here is the outline of my presentation. Introduction, an example, a small example, then I talk about recursive alpha, and I will explain how to schedule recursive alpha programs, and then short discussion and conclusion. So Polyhedral model is a powerful representation of computation for parallel expression and extraction, but it is limited by the expressivity of a fine recurrence equation. So in the literature, some extensions of the model have been proposed, but still representing divide and conquer program is difficult to do in a direct fashion. So there is, for example, a very famous limitation that is that FFT cannot be described using the polyhedral model. And this is something that people have complained about for a long time. So the content of what I'm going to present is to show how we can express divide and conquer algorithm using the polyhedral equational language. So the context is the alpha language. How we are going to extend the language with conditions on the size parameters value. And I will show how affine scheduling can be extended by means of solving recursive equations to compute the parameter-dependent part of the scheduling. So the basic idea is to try to confine the problems to the parameter side, which is the actuality. So here is a representation in a C-like language of a divide and conquer algorithm to compute the minimum of n number. So you start from an array A of n numbers, and if n is equal 1, then you return the value A0. Otherwise, you call recursively this function on the two parts of the array by splitting the array in two parts. Okay, and then you return the minimum. So this corresponds to this structure when n is equal to 8, and you have minimum, a tree actually of minimum operators. So I mean, this is quite simple. Let's see how we would represent in alpha how to compute the minimum number using a sequential program, because currently it's not possible to use divide and conquer. So this is more to explain for people who don't know alpha how it is written. So this is the name of the program in min value. This represents the set of the parameters, the size parameter of the problem. And this is important because that's on the parameter size that will play to give the recursive structure. So we have an array. The result is the minimum, which is a scalar. We don't specify here whether we have integer or whatever. This is all numbers. There is a local variable x, and x is defined recursively by saying that it is 0. And if I is larger than 0, then it's x, the minimum of x I minus 1, and of the element of the array I. And the result is the final value of x. So the syntax of alpha, you have parameter set, you have domains for all the variable, and you have equations like that. So in general, and I'm not going to talk about that, alpha expressions are functional, and so you can do transformation on this equation, and but I won't talk about that. I just use the very simple to read array form of statement in alpha or equation in alpha. So to use recursive alpha, first I have to introduce the call to subsystem, which is already available in alpha. So call to a subsystem is written this way. You have a set of variable that you compute using a call to some subsystem which has been already defined. And here is the important part. It is a function which maps the parameter of the calling system to the parameters of the call systems. And this represents input value of the subsystem. Okay, so f is an affine function. And the only thing we have to add in the language is what we call when clauses, which governs a set of equations that apply when some condition of the parameter are met. So let me show that. If I want to write now the minimum recursive using alpha extended by recursion, here is the base case. So it's not very different from what we have seen previously. So when the parameter value is equal to 1, the minimum is just the first element of the array. And here is the recursive part, which is governed by the condition the parameter that n is strictly larger than 1, larger or equal to 2. And we have local variable here. And we define split actually the array in 2 parts, and we call recursively the minimum on one part and the minimum on second part, and then we combine both minimum. And the important part is that the parameter size here is given by the function that maps n to n over 2. Okay. So now how can we schedule such programs? So let me start by explaining a little in a few minutes how we can schedule a standard alpha program. So if I have a variable v, and v of z is the value of the variable v at point z, so I denote t of v of z, the schedule of v. And if some instance v of z depends on v of z prime, then we need to have these schedules that need to follow these constraints. In standard alpha program, we assume that the schedule of a variable is an affine function of the point, and finding the schedule consists in enforcing the causality in each point of the domain of the variable v using, there are basically two methods. We can use a Farkas method defined by Fautrier, or we can use the vertex method that I've been designing with some other people, like for example, with Sanjay. And in both cases, we are led to an ILP of a few tens of inequalities. So now, if we want to schedule calls to subsystem in standard alpha, what do we do? There are several methods, but this one is simplest to explain. So this picture represents a system which has been already scheduled, and I want to reuse the system in another one. And what basically I'm going to do is I just try to find out the offset of each use of the system and modify the schedule of the input X into the input, the formal, the actual parameter corresponding to the input X by adding the offset D here to the schedule of the input. So that's basically the idea. Of course, the offset can be a constant, but it can be also a function which depends on the parameter, an affine function on the parameter. So that's the idea. And so if we suppose that the subsystem is already scheduled, we gather the schedule of input and outputs, and we add the same unknown expression, and we enforce a dependency between the input-output of the system and the actual value in the calling system. And we run again an ILP program, and we get the answer. So now to schedule recursive alpha, this is basically the idea. And actually, I should say that in the paper, there is some mistakes, and I would like to answer Sven to point out that we made a couple of mistakes. We are going to correct that, but basically the idea is here and it works. So I suppose first that we have a simple recursion scheme. We suppose also that the schedule is unidimensional because we can use multidimensional schedules also for alpha programs. And now the remark I could do is that we cannot assume that the subsystem is already scheduled. So the method basically consists in assuming that the schedule has this form where there is a part which depends on the parameter. And this is a function which is not going to be an affine function. It's a function we have to determine, and that will provide some result in form of a logarithmic expression. So for the equation in the system, we proceed basically as in the standard case. And for system calls, we take into account the parameter mapping function, and we separate the computation of the coefficient tau here and the alpha and of the function phi. So in the base part, what we end up with, at least in the example which are given in the paper, is that we find a recursive equation on the parameter which has this form, and in the numeric example, we get this, which has a solution phi of p is equal to log of p plus 1. So in general, to solve recursive equations like that, there are many methods which are much more powerful than that, and I give reference in the paper where we can find solution to that. Okay, so first, how to represent the FFT. Here is a sketch of the FFT. I mean, basically, what is important is here. The base case is obvious. The FFT of one number just this number. And otherwise, we split an array where we want to do the FFT in two parts. And then this is the equation that splits the left and right part. We call recursively the FFT on the left and right part. And then we have this equation which somehow sketches a butterfly computation. So it's the control is okay, the operation have to be adapted with the coefficient of the FFT. So this is basically the structure of a simple FFT. So we can thus represent and schedule FFT up to the mistake I mentioned. So this has been done using the MMAlpha software. Of course, we can use a divide and conquer approach with other ratio. The static analysis allows checking that the program follows the assumption that I mentioned in the paper. The theoretical complexity of the scheduling is that of ILP, but in practice, it's not a problem. I mean, when we are analyzing programs, the scheduling is not the longest part. And of course, open question that have to be considered is how can we handle multidimensional schedule, mutually recursive programs. And in the paper, we have put some references to other approach of polyhedral recursion. So here is the conclusion that we have been able to do, and future work implement the transformation which are useful in the alpha to transform the program into either hardware or parallel loops, and extend to multidimensional schedule, implement VHDL code generation, and combine, nice idea would be to combine recursivity and reductions to do high-level transformation. Thank you.
Thank you very much, Patrice. We have plenty of time for questions. I understand that you already had some interactions with Sven. So in the meantime, I had a question about the complexity of the approach. So I don't know, I mean, structured scheduling is primarily motivated by scalability and like composing larger problems. So how do you envision the interaction between structured scheduling in a recursive setting in terms of complexity?
So as I said, I mean the scheduling is not really a problem right now. I mean, it depends on what kind of performance you are looking for. But I have here a slide with to show that a typical here is a typical scheduling time. You know, if you get this is one example I've run just last week. If you have about 50 equations, it leads to 1,000 inequalities, and it takes less than two seconds to run the scheduling. So for a compiler, it would be probably too much, but for generating hardware, I mean, this is just peanuts. And for I would say the wrong scheduling on the FFT, because it's not correct. Finding out the 1,000 alpha takes this time, and solving the recursion takes also no time for these simple cases. So I don't know if this answers you.
Oh, it answers, yeah. And this is completely independent of the size of the FFT.
Yes.
Yeah, that's pretty cool. That was the biggest surprise.
So if I may add a bit to that, what you need to do in order to schedule recursive systems is to basically look at two instances or two copies of the system, not instances, rather than looking at the full recursive structure to do the Polyhedral scheduling part of the things. That's why the scalability does not blow up. It should still be manageable into a similar extent as the normal programs.
Okay, we have a question on the chat. So Sanjay is asking, do you actually use Mathematica? So do you use Mathematica as recurrence solver?
Yes. Yes.
Can you say more about this? Because I mean, for people.
Oh, I actually no. I just run there is a function called recursive solver, and I tried a few examples. I mean, it's okay. It gets results of the main theorem given in the Corman analysis books that says, depending on the form, the recurrence, you will get something in log or n over something, and so on and so on. So I mean, it's okay. It's I don't know if it's very fast, but it provides the result. So probably we would have to, if we have more complex program, we would have to look into more details about that. But it just type recursive solver, and it's obvious. I'm not advertising.
No, that was not a general question about mathematics.
Yeah.
I mean, to be fair, the recursions we tried are very simple, so
Very
we have
simple,
to
yeah.
see how it works out with more complex recursions.
Okay, I have a question about code generation as well. So what's maybe I missed part of your presentation, but can you explain a little bit how code generation interacts with this form of recursive equations?
I can. Well, I would like to talk more about generating hardware. It's some special kind of code generation, but Tomofumi could add something about
the hardware is good enough.
Parallel code generation. For hardware, what we do, we transform this all the equation into patterns which are recognizable as either register or connection between data path or controls or multiplexers and so on, and this translation is simple, provided the scheduling has been applied to the equation. So the equation have been rewritten using a change of basis to obtain a new representation, a space-time representation of the equations, and then we transform by backhand this equation into something that can be translated directly into VHDL. So that's basically what you have to do. So I think that applying the change of base in a recursive system is not a problem. I think we should do it and prove it, but because inside a subsystem, we can do that pretty simply. And then a transformation inside a recursive system into a space-time equation, which can be mapped to hardware. I don't think it will be a big problem, but well, we have to do that before to sustain the claim, right?
Makes sense. Yeah. Okay, Tomo, I don't know if you want to add anything.
Yes, I mean, so Patrice has been looking at things from the hardware side of things, and I've been thinking mostly about from the software point of view. And when you do coordination of recursive programs for software, the kind of the schedules that you do across systems are probably going to be implicit in the sense you're going to generate functions and you're going to make recursive calls. So the schedule is implicit. But what I'm looking for with the recursive programs is that now you have a new space to explore by how you can decompose programs into divide and conquer strategies, which, you know, the FFT is a very basic example. So extending something that the spiral does for linear transforms to general affine programs was what I was looking for, rather than just generating code for recursive systems. So it was more about how do you explore the decomposition, which I am interested in. The code generation itself is probably going to be generating a function for each system and then making recursive calls.
Yeah, you may have some interesting like scoping issues if you don't want to have a single assignment structure that crosses.
Yes.
That's going to be interesting.
There's memory management that is tricky.
Yep. Great. Looking forward to it. I've not looked at recursive programs in the last 13 years, but all in 14. Oh, sorry, there's one more question from Sanjay. Do you want to ask the question?
Oh, I just made a comment that you can benefit a lot from the work on tail recursion optimization used in the functional programming community, because you may at times not want to implement this as a function call and avoid it. Yeah, avoid that overhead.
Yeah.
All right. No more questions. We still have time. If not, I'd like to thank Patrice again. And now we have time for a break. That's the standard HiPEAC break. So you're free to join whatever HiPEAC activities there are, or join the Gather town, the Gather space. So thanks, Vincent, for just sharing the link again.
Can you send a link to the Gather space? Oh, there it is. Okay, thank you.
It's again in the chat, yeah. Or do whatever you want, and we reconvene in 30 minutes. And Arvind will be checking the next session.
I will just pause the recording, but keep the Zoom session on so that like you can just stay here.
Thank you.
I guess we can start. Hi, everyone. Welcome back. So the next presentation is from Sanjay on the topic of simplifying dependent reductions. So,
all right. Thank you, Arvind, and welcome everybody. It's good to see people even virtually, but it's really nice to be back at Impact. So I'm going to talk about something that I picked up after a gap of about 15 years, and I want to sort of motivate what we were doing. Okay, so normally when you write a program, you develop algorithms, etc. You have some problem, and then you come up with an algorithm for it, and then you write a program, and then you have an optimizing compiler that gives you an improved program. And the best that the optimizing compiler can do is to give you a constant factor improvement, or give you an improvement by a factor which is comparable to the number of threads or parallel processors if the optimization is in the parallelization. Okay. But no optimizing compiler changes the complexity of the program. Okay. On the other hand, when you apply techniques like simplifying reductions, and this is why we were excited about it 15 years ago, is that when you apply such a technique, what you're doing is you are actually improving the asymptotic complexity of the algorithm. Okay. Of course, you cannot do that for arbitrary programs. We have to be domain specific. And indeed, we are very, very limited in the kinds of the programs that can benefit from this technique. So let me recall for you a little bit about what is a reduction. A reduction is an associative and commutative operator applied to collections of values to produce either a single or collections of values. Okay. The techniques that I am describing over here are applicable to reduction operators that are also commutative. This is not strictly necessary. Reductions can be defined when the operator is only associative. For example, if the operator is a matrix multiplication, then it is associative and not commutative. And then these techniques that I'm describing become limited. For the most part, though, their operators are associative and commutative, especially if you see them as sort of elementary arithmetic operators. Okay, so the collections that we are dealing with are polyhedral sets. It's not, it's not a surprise. And I'm also going to tell you that in this talk, I'm going to use mostly pictures to describe what we are doing. And polyhedral sets are relatively easy to describe with pictures. So let's look at this simple program. It is a doubly nested loop. It computes an array yi for a range of values of I. Okay, and the ith value is the sum of the first I elements of an input array X. Okay. In other words, it is computing this equation, and it's well known that this is a prefix sum program. And the code that I showed you at the bottom is something that takes quadratic time to compute because it's a doubly nested loop, and each one can go, is linear with the size parameter n. Okay, and of course, no one writes such a program. They would write this program incrementally because they would compute the yth answer from the y-1th answer with just one operation. Okay. Now this is, of course, a deliberately simplified example, and we may see a few that are slightly more complicated in this talk, but basically what we want to do is to try and go from this quadratic time program or a higher complexity program to a simpler program which has lower asymptotic complexity, and we want to do it optimally and automatically. Okay. All right. So here's the outline. What I will talk about is a large part of what I will talk about is to recap the previous algorithm that did simplification of reductions when the input variable, the variables or the expressions that were being read did not depend in any way on the output variables of the reduction. Okay. And then when we go to dependent reductions, we'll see what happens. And then we'll coupling, we basically will need to couple scheduling and simplification. And I will explain how we do that. Okay, so there are three equivalent representations of these programs. You can look at these as pictures or polyhedral sets. You can think of them as loop programs, or you can think of them as equations. And they're all equivalent, but the ideas that I want to talk about are best explained when I use pictures. Okay, so here is a program that computes a one-dimensional answer yi, and each answer is a double summation of some value fijk. So the f is sitting in this pyramid, and I am taking a two-dimensional slice of that and accumulating that to produce a single scalar answer. And in this case, that is the set of triangles. So all the values of f at all the points in a triangle contribute. I hope you can see my my cursor. No, you probably don't. I have to look at the other screen. Do you see my cursor now?
Yes.
Okay. So everything in this triangle is accumulated to produce this answer. And similarly, everything in this triangle is accumulated to produce this answer. Okay. So we have polyhedral sets. Now I want to talk about two very specific affine functions. One is the function that represents the accumulation, the function that maps all the points ijk to the point I. Okay, so it's the mapping from the iteration space or the domain of the expression to the result space, and that is an affine function, and of course it is a many-to-one function, and that's exactly why we have a reduction. Okay, there is also a read function at every point in this iteration space or in this pyramid. A value is being read, and in this example, the value is distinct at each point in the iteration space. I am reading f of I, j, k. If that's the case, if there is no possible reuse, if the read function is not many-to-one, then we might as well go home. There is no simplification possible. If every value of f is distinct, then a cubic amount of values have to be read, and that is the input complexity. There is no hope of reducing this. Okay. So the interesting problem of simplification arises when there is reuse, and the reuse in the polyhedral compilation is basically the null space of some affine function. Okay, so here's an example where the reuse is spanned by the ij axes, because f of ijk is simply reading the kth element of an input array x. Okay, so everything that you see in the ij plane, which I have shown in green, actually evaluates to the same value. Okay, and so now, because many values that contribute to different answers are actually identical, there is this reuse that can be exploited, and because of that reuse, maybe you can do the computation much more efficiently. How do you do it? Well, you choose a basis vector of the reuse space, okay? And so we choose this green arrow that I'm showing over here, okay? If you translate one of the slices along that green arrow, what you observe is that a large part of the adjacent triangle is already covered by the values in the smaller triangle, in the purple triangle. And I know that sometimes the purple and the blue look similar. So a large number of values that contribute to the triangle on the right are also identical to the values in the triangle on the left, which means that instead of actually accumulating all those points, we might as well use the result of the previous accumulation. Okay, so this says that basically the answer over here can be computed by taking this answer and using only the values on this line at the bottom. Okay, that's the whole idea. You are you're reusing data values that are identical, and you use that to reduce the complexity. Okay, what happens here, and you're then, so all the computation that is inside the interior of this pyramid goes away, and you are left with only a residual computation that's on the bottom plane. Okay, so what you have done is you have taken that pyramid, you've translated it along the reuse vector, and you've done some manipulation, and you're left with one of the facets of that. Okay, now remember that we had reuse in more than one direction. There was a two-dimensional reuse space. So even amongst the points in the bottom triangle, there is further reuse. The values on one of those lines could be identical to some of the values on another line parallel to it. And indeed they are. So there is one more residual reuse direction left to exploit. And so what you can say is that by exploiting this reuse in this direction, as per the green arrow over here on the bottom face, you can compute that final blue answer by taking the partial answer that we had computed in purple and accumulating it with only one single point. So what you have deduced by this is basically that this whole computation, which was cubic, is actually the prefix sum of the prefix sum. Okay. All right. So this is multidimensional simplification. There are multiple dimensions of reuse, and this is what you can exploit. Okay. The problem is when you want to exploit this reuse in an automatic way, if the reuse space is more than one dimensional, then there is an infinite space of reuse vectors to exploit. And the question is, how do you navigate this space? Okay. For example, instead of the first choice of reuse, what if we chose the reuse along the horizontal direction as our first transformation? Then moving this left triangle in that direction to the right one will overlap, as you see on the right side, and the residual computation is on the front triangular face of the original space. Okay. So the question is, how do you navigate this space and how do you do it optimally? Okay, and let me explain the algorithm that we had 15 years ago, which is basically first you do a pre-processing and you determine what the reuse space is. Okay, and what you also do is to construct not just the entire domain, but also the entire face lattice. That means the facets, their facets, and so on recursively. Of the domain of the body of the equation. Okay. All right. And I'm taking this example. This is a two-dimensional example. There is a lower bound, which is from j equals I, and the upper bound is j equals 2i plus n. And then also there is another upper bound, which is exactly 3n minus 1. And this illustrates sort of different conditions that might happen. Okay. You pick a reuse vector, you translate the domain along that direction, rho, and you delete the intersection, and you retain residual computations on the different facets. Okay, and then you label each facet according to certain properties. Okay, independent of what the chosen reuse direction is, there are certain facets that are boundary facets, and they are boundary facets because when you project them along the accumulation, you end up with a boundary of the result. So the purple vertical facet and the gold or the yellow vertical facet, because our projection is along the columns, are boundary facets. Independently of the boundary facets, you also label facets that are, relative to their relative to the reuse direction that you've chosen. They are either inward, outward, or invariant. The black facet on the top is invariant because the reuse direction here is horizontal and the black facet does not change. The blue facet is an outward, is an inward facet because when you move it, you move inside the domain, and the red facet moves outside. And basically the algorithm consists of accumulating all the inward boundary facets, add the inward facets to when you reuse, and you subtract the outward facets, and then you recurse only on the remaining facets. Okay. All right. So there are only finitely many choices, and all choices yield the same facet labels, are equivalent for the complexity reduction. So although there is an infinite space, you can navigate this space by partitioning the reuse space, reuse vectors into how they affect the facets. That's all that is needed. Okay. So now for the new problem. What in all of this assumed that the input variable that you were reading was completely independent of the output variable. Okay, so I take my same reduction in this two-dimensional space. And I say, what if I have this new equation? X of I depends on Y of I minus 1. This should excuse the typo. It is, X of I is a function of Y I minus 1. Okay. Then out of the two different reduction phase, reuse directions to exploit, one of them becomes illegal because it introduces a cyclic dependence. If the reuse direction that I choose to exploit introduces eventually a new dependence on which result is used to compute the current result. So the projection of that reuse vector by the accumulation function is a new dependence vector in the program. It was not there in the beginning. Okay, so as you do this reduction incrementally and you pick these reuse vectors, you're introducing new dependencies, and the question is how to do this in a clean way. Okay, so not all reuse vectors are legal, and you might end up with cyclic dependencies. Okay, so the main thing that happens is that you now have to couple the simplification problem with scheduling, and polyhedral scheduling is well known. Okay, when the dependencies are given, but what do you do when the dependencies are not known and are introduced incrementally as the simplification proceeds? Okay, so the key insight is that the feasible space of all legal schedule is a finitely generated, that means with 1 to m, there is an m number of generators. Blunt, that means it does not contain the origin. Cone, the feasible space of all schedules is a cone, and that's the key thing. Okay. And again, this idea is also not new. There was a paper from Delhomme and Ibsen in 1985, which talked about, in the context of systolic synthesis, they talked about time cones. Okay. All right. So if it is, and it's, it's easy to show that it is finitely generated. That means there are a certain number, a fixed number of generators of the cone, and it does not contain the origin, because if it contained the origin, then it would not be a legal schedule. It will be only a legal schedule where the program has no dependencies and everything is computed at the time step 0. Okay, so we start with the feasible space of all schedules in the original program. Okay, when choosing the reuse vector at any phase, what you do is that you make sure that this feasible space, together with the new dependence that you're thinking of introducing, does not become empty. Okay. Because if it becomes empty, then you will not find a schedule, you would have introduced a cyclic dependence. Okay. So how do you do that? Basically, at least one of the generators satisfies that theta I rho is non-negative. Okay. And therefore you have m disjunctions that are now going to affect the choice of your feasible space as you recurse in the algorithm to pick, to traverse the phase lattice. Okay. But again, just like we showed 15 years ago, the space of, it's still possible to partition the space of all the feasible reuse vectors into equivalence classes. In this case, at each level, it becomes m-fold larger. And so you have to do a backtracking search, but you still leads, you have finitely many choices and you retain the optimality of the algorithm. Okay. I don't know why I have this slide again. I'm sorry. So I want to leave time for questions. So I want to point out that there are actually some very interesting early papers that talk about this. So I strongly urge you to read Bhavani Roy Chaudhary's 1988 PhD dissertation. Some of the stuff that he did in that has never appeared in any conference or any journal. So you have to go to the source. As far as I know, he was the first one to introduce this idea that if you have a many-to-one write in some sort of an affine space, then what you are doing is actually a reduction. And that idea was then picked up by Hervé Leverge, who introduced reductions in the alpha programming language that was developed by Morris. And as I mentioned earlier, Delhomme and Ibsen in 1985 were the first who observed that the feasible space of schedules was a cone. I also want to highlight a paper that came up, that's very recent. So this was all sort of 35 years ago, and now we moved to 6 months ago, or no, actually literally coming up in a couple of days. So there's a paper in Popl 2021, and I think it is scheduled for presentation day after tomorrow by Yang, Atkinson, and Carvin. They were the ones who actually first to formulate this problem of simplifying dependent reductions. They came across this problem because they have a very large number of use cases that came from probabilistic programming. And in those algorithms, and if you're building high-level tools for probabilistic programming, and statistical Bayesian learning in particular, the algorithms are formulated as mathematical equations, and if implemented naively, they lead to these computations that have reductions with the possibility of simplification. So they have a fairly large number of practical use cases. Okay, what they did was that they formulated this problem as a bilinear programming problem. They basically said that, okay, we are going to choose all these reuse vectors rho independently and simultaneously. So they have a very clever formulation in which they simultaneously formulate the reuse on all the faces of the phase lattice. And then they couple that with the scheduling function. And then they say that basically the schedule vector of the schedule times the projection function times the reuse vector must be non-negative to satisfy causality. Now, in this formulation, what happens is that the theta, the schedule, is unknown, and the rho is also unknown, and so this becomes a bilinear programming problem. And so, the very large number of variables and the fact that it's bilinear makes it really intractable in practice. And so they don't further do this. They actually give a very simple heuristic that works in practice. Okay. So in conclusion, simplifying reductions has practical benefits. Dependencies add a new twist, and it requires now whole program analysis, not just one equation. And yet we can have optimal simplification even with the dependencies. Of course, this is work in progress, so we haven't done an implementation. We don't have empirical results or anything. So that's where we are. Thank you, and thanks for your time. And I'm happy to take questions.
Thanks, Sanjay. We already have 2 questions. So Vincent, maybe you can explain the question. That would help.
Can someone repeat the question, because I'm not seeing them?
Sure. So
I'm manipulating my windows to get out of the. I have to stop sharing.
No problem.
Leave the slide, Sanjay.
Okay.
On slide 18, I had a question because you showed 2 different ways to reduce, to simplify.
Yes.
this 3D to 1D problem. 18.
Yes, this one. So I had previously simplified by exploiting first reuse along this oblique direction, which led to a residual problem on the bottom face or bottom facet of the pyramid, and then the second direction was like this. Okay. Alternatively, the first simplification could have been done along this direction. Okay, leading to a simplification, the residual computation on the front face. And even on the front face, there is some residual reuse, and even that can be done. And I didn't go into details, but that can also be done. Okay.
But if you do this last step, don't you get the same result finally?
Yes, asymptotically, that was exactly the point. Regardless of the choice of the reuse vectors to exploit, you will always, and in this example, the operator is addition, and addition admits an inverse. If the operator admits an inverse, then what happens is subtraction operator is always allowed. Okay, that means basically in this entire linear space of possible reuse vectors, anything can be chosen, and you will always be able to eventually reduce the complexity. And so all directions of reuse that are in the original program can be fully exploited, and you get maximal reduction of complexity.
So the order and the choice of those vectors is
not matter.
Doesn't matter. Finally.
Yes. The tricky part actually happens when the operator does not admit an inverse.
Okay.
So for this example over here, if the sigma is replaced by max, okay, then no simplification is possible, strangely enough, because the max does not admit an inverse operator. So if you use simplification by exploiting reuse to the right, here there's only one dimensional, so the only choice is go to the right or go to the left. If you go to the right, the bottom oblique face becomes a subtraction. Okay. When you have an operator that does not admit an inverse, the feasible space is basically constrained such that there is no facet with an outward label. There must be no facet, so that instead of being the feasible space being the entire linear space, it now becomes a cone. There are additional constraints that that limit how it can be used, and even in that limited space, you can partition it into partition the set of reuse vectors to use into equivalence classes.
Okay, thank you.
Okay.
The next question is from Prashant. So basically, he was asking about the use cases for dependent reduction. He was thinking about stencils and LSTM.
I have not thought about LSTM, but I don't see. So when you say stencils, are you talking about situations in which the coefficients of the stencil, so basically you're doing some sort of a convolution, and the coefficients have some equality along a direction? Maybe the stencil coefficients are all, let's say they're symmetric or something like that?
So Sanjay, I was more asking about the time iterated stencils. For example, in a single stencil, so a single output is produced by the multiple partial sums, but that accumulation is not necessarily dependent on the output value. But whereas in time iterated stencils, we might need previous output values to compute a new output value.
Okay.
So I'm trying to see what benchmarks or what algorithms exhibit these dependent reductions.
Okay. So actually, even before dependent reductions, is there a reduction that exhibits reuse, that the value of the expression that is being accumulated, the value is the same at different points?
Okay.
So that I don't see in sort of stencils or uniform dependence computations.
I see. Okay.
I know I was trying to, grasping at straws, I was trying to think that maybe if the coefficients have some, some pattern. So there are sometimes, image processing filters that are called separable filters. So the coefficients can be expressed as the outer product of a column and a row or something like that. In those cases, the result at any point ij can be computed not by a double summation, but by two single summations.
Ah, I see. Okay, I see what you're referring to.
Right. So that is the sort of complexity reduction that you get in simplification.
I see. Okay, that explains. Yeah. Thank you.
Okay.
Okay. So we have one last question from Brendan. So are there scenarios where this kind of optimization might not work well in parallel algorithms? Basically, large amount of sharing information.
That is actually a very nice and very interesting question. Take my first starting example, a prefix sum calculation. The original program, which was quadratic, which was unacceptably complicated, complex. Okay, that had very nice parallelism. Every result can be computed independently. If you introduce the dependence from the previous, so you compute one answer based only on the previous answer, now you have introduced a dependence, and if you go apply standard scheduling techniques, this becomes inherently sequential. But fortunately, prefix sums, people have spent a lot of time, and we know how to parallelize prefix sums basically using divide and conquer. And so, it might be interesting to use this as an example with Patrice on the recursive polyhedral computations. So that's a very interesting direction to pursue. Good question.
Thanks. We are running out of time, so we can continue the discussion on that.
Thank you very much. I'll stop sharing.
So let's thank the speaker. So the next talk is from Aditya Datri and Benoit Mester on static versioning in Polyhedral Model.
Hi, everyone. Should I share my screen?
Yes, please go ahead.
Awesome. Can everyone hear me okay?
Yeah.
Can everyone see my screen?
Yep.
Okay, awesome. So today I'll be talking about static versioning in the polyhedral model. And this is joint work with Dr. Benoit Meister, my colleague at Reservoir Labs, and we've been working on this for the past few months. So here's an outline of my talk. So first, I'm just going to briefly describe the kind of work that we do at Reservoir Labs. Then I'm going to move on to the background and motivation for polyhedral versioning. Then I'm going to describe our approach to versioning, which was implemented in RStream, our polyhedral compiler. And then I'm going to show some results that demonstrate the benefits of polyhedral versioning and show that it does not incur too much compilation time overhead. So Reservoir Labs is a small technology and solutions company headquartered in New York City. And since 1990, we've been working on cutting edge problems in areas like high performance computing, specifically advanced compilers, networking, cybersecurity, and algorithms. If you'd like to check out some of our work, I would encourage you to visit our website here or contact us via the email provided here. So now moving on to background and motivation for polyhedral versioning. So versioning, also known as multi-versioning, what is it? Well, it's based on the observation that different optimization opportunities arise under different runtime conditions. With versioning, the compiler generates two things. One is multiple versions of a code region, and two is code to select the most appropriate version at runtime. Here's a traditional example. Suppose alias analysis cannot statically disambiguate two pointers, P1 and P2. Then the compiler might decide to insert a runtime test that checks at runtime whether P1 or P2 are aliased. And depending on whether the test holds, the code can execute different versions that have been appropriately optimized to those cases. So for example, if the pointers are not aliased, then in principle, more instructions could be run in parallel. And this kind of work was shown by Sampaio and others in 2017. Now, what motivated us to consider versioning? Well, it's basically deep learning optimization. We came across DL networks that can reuse layers with varied input tensor sizes. And this was through building a TensorFlow front end to RStream, which we call TFRCC. We observed that RStream, our compiler, maps differently for different fixed input sizes. And here mapping refers to the Polyhedral Compilation's optimization phase. And now more and more DL networks have variable size inputs. And assuming that sizes are parameters to the optimized function or the function to be optimized, we may not know anything about these inputs or the sizes of these inputs because they might be defined at runtime, for instance. And a single mapping or set of optimizations cannot be optimal for all sizes. And so we need to be adaptive to these sizes. And so our solution is polyhedral versioning. In particular, we consider a function, func, where we have input parameters a1 through an. And these a1 through an are runtime defined parameters. And for example, they could be tensor sizes. And given this function, we would like to generate two things using our Polyhedral compiler. First is different versions of func, namely func1, func2, func3, which have been optimized over different affine parametric domains over a1 through an. After having these versions, the second thing we would like to do is to generate a wrapper function, version func, which takes in the same parameters as the input function, a1 through an, but this conditionally calls the different versions, func1, func2, func3, after checking the runtime values of a1 through an and seeing which affine parametric domain they lie in. And this is sort of a formalization of the problem that we're considering in this work. Now, there are other approaches to optimizing towards runtime values of parameters for a function. One approach is to let the user incorporate knowledge of runtime parameter values into the program logic. RStream allows for this very explicitly through the use of a pragma preprocessor directive, as shown here. But the issue with this is that it places burden on the programmer, and it's not automatic. The second set of approaches is just-in-time or JIT approaches. With PolyJIT, we can find runtime polyhedral cases and apply pointwise versioning. And with Apollo, we can use runtime tests to apply or to assemble code fragments into optimized code. And more recently, in 2020, Apollo has provided runtime versioning support. However, the issue with JIT approaches is that they're limited by the need to minimize compilation time. And it's, in general, combining JIT with the polyhedral model could be expensive. And this motivates the need for an ahead-of-time approach, such as ours. Before I move on to the approach, I'm just going to go over the polyhedral intermediate representation, or IR. On the left are the polyhedral terms, and on the right are the functional terms. So first, we have what's known as a generalized dependence graph, or GDG, and this corresponds to a program function. The parameters of a GDG correspond to the formal parameters of a program function. Then we have what's known as a GDG hierarchy, which corresponds to a function call graph. And the parent-child GDG relationships in the GDG hierarchy correspond to the caller-callee relationships. And then we define what's known as a specialized or version GDG, and this corresponds to a version function. Finally, we have what's known as a context of a GDG, which corresponds to a function domain or preconditions applied to the function. And the context of the GDG is realized as a set of affine constraints over GDG parameters and is used by the Polyhedral compiler in making its optimization decisions. Now, coming to our approach. Our approach has three main steps. The first step is to auto-generate useful GDG parameter domains for versions. And while this can be done in any pass of the Polyhedral compiler, we chose to do it in the process replacement pass of RStream. The second step is to incorporate and code these versioning decisions into the mapping process. And finally, we must generate the version code. So the goal of the placement pass is to associate a placement function to each polyhedral statement. That is, we have a function PL that takes in the GDG parameters and then the enclosing loop iterations and outputs the grid coordinates where the polyhedral statement is placed. And the GDG parameter values are from the GDG, which includes the polyhedral statement. Now, the pass performs what's known as an occupation test. And this test basically checks if the loop trip count is at least C times the processor grid size. C is a constant, which we refer to as the occupancy, and it's the factor by which we want to occupy the grid. If the test holds, then we place along the loop. Otherwise, we try another loop. When the trip count involves unbounded GGG parameters, the mapper assumes that they're large enough, which is an unchecked assumption. So here's our solution. Let T of n be the parametric loop trip count, and let Pg of k be the grid size along the targeted dimension k. When T of n cannot be bounded by a constant, then we schedule the mapping of a GGG version, and we quote-unquote tell the mapper to consider the following range. That is, this range is, it's saying that the parametric loop trip count is at most C times the grid size. And this corresponds to the opposite of the assumption that the placement pass was making. That is, this assumption, this range corresponds to making the assumption that of not large enough. And now it remains to define what quote unquote tell the mapper to consider following range or consider a fixed affine range means. And that brings us to step 2. That is encoding the versioning decisions into the mapper. So we introduce a polyhedral statement called a specialized op, and this maintains versions of a GGG, which we previously defined as specialized GGGs. We also introduce a specializer GGG to hold a specialized op, and that's its sole purpose, really. And at cogen, this GGG will be lowered to a function, the wrapper function we saw earlier, that conditionally calls the version functions. A specialized GGG comes from specializing a GGG. That is, we can clone the input GGG and intersect the clone GGG's context with the given domain. Here, the given domain will be the parametric loop trip count being at most the C times the grid size, as we saw in the previous slide. Now, in order for the mapper to keep track of the specialized GGGs that are created, it must be inserted into the existing GGG hierarchy. So we can see here in figure 1, suppose we're trying to specialize GDGG. P is the parent GDG, C1 and C2 are child GDGs of G. So if we specialize G to get the specialized GDGG prime, then that leads us to figure 2. And here we can see that a specializer GDG D was created, and then the G prime was created, which was a clone of G. And as such, of being a clone of G, it has the same children, C1 and C2. And now D here, the specializer GDG, is in between G prime G and then P, the old parent. And the reason for this is that we, in the lowered program, we don't want anything to call the version functions directly. We want them to go through the wrapper function and let the wrapper function call the version functions. And that's why D serves as an intermediary between P and G prime and G. Now, if we were to specialize G prime or G again, then we would make minimal changes to the GDG hierarchy. And that brings us to figure 3. So if we were to specialize G prime or G to get G double prime, then we would just simply tack on G double prime as a child of D, and then have a G double prime have children C1 and C2. So after insertion, the specialized GDG must be scheduled for mapping. And we decide to start the mapping where it was at the point for the input GDG. And in this particular case, we do it right at the placement pass, since that's where the creation of a specialized GDG was invoked. Now, coming to the code generation, our goal is to generate nested if-else statements for the specializer GDG that, 1, avoids explicit polyhedral differences that can lead to ugly code and complexity, and 2, executes only one version for any set of parameter values. We note here that there's an extra degree of liberty when the specialized domains overlap, and we don't exploit this in this work. So the naive approach would be to check each GDG's context. So here CI is the context for specialized GDG GI. And so we would check the constraints of the context against the runtime parameter values, and then call the GDG whose context is satisfied at runtime. However, the issue with this approach is that there can be redundant checking of constraints if the context share constraints. And to get to GI, get to the function call for GI, we would need to check all the contexts that are leading up to GI. And that can create overhead. And so it turns out we can do better. And so our idea was to, for the outermost conditions of the branching, we can pick a constraint that divides the context non-trivially into the contexts that are included by the constraint and the contexts that are not included by the constraint. And sort of the following properties arise after some more formalization. So no constraint is checked more than once for any parameter values, in contrast to the naive approach. And the total number of constraints to get to GI is less than or equal to n plus the number of constraints in its context. So here n is the total number of contexts or total number of specialized GEGs. And we sort of refer to the proof for a more detailed proof and formalization of this algorithm. And in picking this constraint, if we pick a constraint that evenly divides between included and not included, we can drive the n here to log base 2 of n. As close as possible to log base 2 of n in the upper bound. Now, coming to the results. So our test machine had one socket, 8 cores per socket, and 2 threads per core. And the processing grid size was 16, basically a linear grid of 16. And then we had 3 test programs, which were all neural network layers. So FC is a fully connected layer where input-output sizes are equal. Convolution GoogleNet is the first convolution of GoogleNet. MaxPool ResNet is a residual neural network layer that uses MaxPooling. Here, the test programs are functions that have one runtime defined parameter. So if we saw from earlier, we had A1 through AN, we just have A1 here. Here, the version code is branched on this parameter's value. For small parameter values, the version program executes further optimized code. And for large parameter values, the version and non-version programs basically execute the same code. And here's our testing procedure. So we did this on the OpenMP target of RStream, and we had implemented versioning into RStream for doing this. So for each layer, occupancy setting and param value, and here by layer, I mean the test program. And by occupancy setting, I mean the C value, the constant, which was mentioned earlier in the placement pass. So for each of these combinations, we can compile the program with and without versioning, and then we can run the version program with a fixed parameter value for 5 trials. And this is to dampen OpenMP variability. We can do the same thing with the non-version program, and then we can compute this runtime speedup. And the occupancy values that we use are 100% and 200%. And 200% is to leverage dynamic load balancing of OpenMP. And this is sometimes referred to in literature as over-provisioning. So here are the results. So on the left are the results for FC with 100% occupancy. And on the right are the results for 200% occupancy for FC. And we can see here that for small parameter ranges, there's a significant speed up. All these numbers are significantly bigger than 1. However, for the large parameter ranges, we sort of see the same performance between versioned and non-versioned code as the values are close to 1. And we see the same sort of result for the other layers. That is, we see a significant speedup, and then speedups close to 1 for the large parameter ranges, and same here. And so what's the theme here? So the speedup that we are seeing was due to a sequential version being executed by the version program, and that being faster than the parallel version of the non-version program for small parameter values. And this is expected because there's a certain initial cost for parallel code to execute. And the example layers that we had sort of resulted in a tug of war between sequential versus parallel code. It would have been more interesting, perhaps, to have the version code generate parallel code instead of sequential code. And thereby, we have a comparison between parallel code and parallel code for the small parameter values. It would have been more interesting to see what the results would have been in those cases. And the bump, that is the significant difference between the speedups and then the tapering to 1, the bump between versions, that can be explained by the versioning domain inequality and then the occupation test. So here, the inequality can be improved, and the test is very simple but not optimal. And that sort of explains the reasoning behind the bump. And we chose a simple target, OpenMP, and a simple pass, or fairly unsophisticated pass process replacement. And this was useful to understand the basic problematic, but obviously more trade-offs and more complex questions will arise with other passes and targets. And we leave this to future work. coming to the compilation time overhead. So we tried compiling all the layers with different occupancy settings, and the values, the slowdown seems to be pretty close to 1, which suggests a very low overhead. And this sort of is the result of choosing to start the mapping for a specialized GDG right at the placement phase or placement pass. That is, do a partial mapping instead of a full mapping right from the beginning. And while we were with the full mapping, we would have been able to exploit more optimization opportunities, but the compilation time would have been higher. And sort of this is a trade-off to explore for future work. At this time, I want to thank the Department of Energy for their funding, which made this work possible. I wanted to thank the program committee for giving us very helpful feedback on our work and giving us the opportunity to present here today. And I wanted to thank you all for listening, and I'll be happy, and I think my colleague Benoit is also in the audience, so I think we'll both be happy to answer any questions that arise in Q&A. And here's a list of references.
Thanks, Aditya. So we have one question from Philip. What about the final code size? Do you set some limits in the number of versions? If yes, is it an actual limitation of the approach?
So as far as the code size, in the versions or in the programs that we ran, the code size of the sequential version wasn't too much. Like it wasn't that big. If I were to recall from memory, I think it's about like maybe half the size of like the code for the parallel version. So I guess in this experimentation, we didn't see that limitation of code size. And I think there was a second part to the question, right?
One thing is, if I may add to that, it's so some embedded targets will be sensitive to that issue, and actually it's not a new issue. It's an issue that appears in every attempt to do versioning by a compiler. But currently there is a way to stop versioning when we think we already have a lot of versions. It's not a very precise test. One of the issues is that it's very hard to predict the actual code size from within the polyhedral. So I think effective approaches to that are based on auto-tuning. So trying some limitation parameters and reducing the code and looking at code size.
So yeah, so there is a related question also from Alex, like how do you choose the specific parameter range for which the layers are specified?
So you can go ahead.
So a range can be provided by the framework, so the TensorFlow front end, for instance, in our case. If this is known in any way, so that's if you go up Aditya in the other approaches slide, that can be generated along with the code definition with the pragma here. You can say you can give a range of values for n here. This can be it's just a polyhedron. So I guess that's part of the answer. Otherwise, if we don't know, we don't know, and that's where versioning becomes useful. It is to find a good heuristic. And right, we're presenting placement here, but often the problem is more complicated.
Yeah, that's why I asked, because it might be tiling or something. And if you look at ResNet, you get plenty of weird sizes. That's like even libraries are not optimized for. So that's why I asked, like,
That's right.
Do you hard code ResNet sizes, or is there something?
So, yeah. I mean, the ResNet versions we've worked with are frozen, and so those only present fixed size.
Okay, I see. Thanks.
Fixed size, right. But it's not always the case.
So I also have a related question. In slide 20, can you please go to slide 20? So here, like, there are 3 test programs and like 1 runtime defined parameter. So what does that runtime defined parameter change? Is it like batch size or?
Sure, yeah. So I guess like in the case of FC, it was the input vector length. In the case of convolution GoogleNet, it's the number of images handled per batch. And in MaxPool, it was the height of the input image.
Okay, thanks. So we have one more question from David. Like, basically the question is, you ran each program 5 times to control the variability. He's asking whether, like, how do you compare the best of 5 runs versus the worst of 5 runs?
So I think what we did was we just took an average over the 5 trials, and sort of like, because there were a few number of programs, I was able to manually see or check that there wasn't too much variability. So taking the average sort of made sense.
So mainly the question is like, what is the relative magnitude of variability versus your speedup?
Yeah, I don't think there was too much variability. So
okay.
I think speedup was significant.
Yeah, we haven't formally gathered that, but overall the variability wasn't great. Obviously, it is probably higher in the smaller sizes, especially in the parallel cases. But right, so we don't have the numbers. Is the answer.
Yeah. So also, like, one comment from Philip is that, like, Apollo does not use runtime test to assemble the code, but basically it uses Pluto on the fly to generate the code. So it's just a comment from him.
Oh, I see.
I think it might depend upon the version of Apollo, right?
No, we always, like, I was also the author of Apollo. So yeah, we always directly pass it to Pluto, and Pluto is the one which creates. Unless, like, the newer versions does something different, but yeah.
Okay.
So
thanks.
Let's thank the speaker again. So sorry, I was muted. So yeah, so the next talk is from Anshuman, Prashant, and Puan Sai. I'm not sure I'll pronounce the name correctly. Sorry for that. The talk is on hardware abstractions for targeting Edo architectures with the polyhedral model. So the authors have sent a live recording of the same. So and I can show that one, or does the authors prefer to do the live one?
No, why don't you go ahead and show the recording? I'll take the questions at the end live, of course. We don't have technology for doing recorded questions yet.
Sure, let's do that.
Hello, everyone. My name is Anshuman Parashar. I work at NVIDIA, and I'm delighted to present this work on hardware abstractions for EDD architectures. My co-authors on this work are Prashant Chattarjee, who now works at IBM Research, but did this work when he was at Georgia Tech, and Puan Sai, also from NVIDIA. Data movement is becoming an increasingly larger problem. And typically when we think of data movement, we think about things like DRAM energy. It's not just that. If you compare the energy it takes to perform a multiply with the energy it takes to fetch the operands for that multiply even from an on-chip SRAM, there's an order of magnitude difference. Here's another way to look at it. If you look at the energy stack for a gem layer that's mapped onto an accelerator architecture, you can look at the energy stack and see that only about 20% of the energy is consumed by the MAC. The rest of it is consumed by data staging and data movement across various levels of the architecture. So one of the ways in which these costs can be reduced is by using this approach called EDD, or explicit decoupled data orchestration. So to understand how these architectures work, let's compare them versus classic CPUs or GPUs, which we categorize as ICTO, or implicit coupled data orchestration architectures. So here's an example of a simple organization with DRAM and 2 levels of cache and a set of data paths. So how does a typical program work? You sort of have a program binary running on a data path. It needs some data that it doesn't have, and it issues a request, a load instruction, which goes to a cache. The cache misses, and it's going to filter that instruction all the way through the last level of memory, and the data is eventually going to come back to the requester. The reason why this is implicit is because the programmer only issues a load instruction, and all of the staging of the data is managed implicitly by the hardware. So this is very easy to program, but it needs sophisticated pieces of hardware to manage the flow of data. In contrast, in an EDDO architecture, explicit decoupled data orchestration architecture, notice that in terms of organization, I've picked almost exactly the same organization as the ICDO architecture with a DRAM and 2 levels of intermediate storage. However, instead of caches, these storage elements are now scratched by buffers or register files, which means they need to be addressed and managed explicitly. And so the way an EDDO architecture manages them is by having a distributed set of state machines that perform a variety of functions. And instead of having a single fat binary doing everything, you have a distributed set of much smaller and efficient binaries scattered throughout the architecture. And all of these distributed state machines are programmed with these binaries. And together, they work in concert to execute the algorithm. So how does it work? Your state machines, such as address generators, can pretty much run ahead if it's a statically known address pattern and start generating addresses. And if the moment data becomes available, the data can start flowing through the architecture and sort of pushing its way through to the data path, so that the data path really doesn't pull or issue any load instructions. It just uses data coming in on channels and is able to use them as they're available. So there are certain benefits of this approach. The benefits are that these dedicated and often statically programmed state machines are more efficient than general purpose cores because they're built to do very specific things. The notion of prefetching is almost non-existent because you're perfect fetching all the time. As I showed in the cartoon, these state machines are running ahead and pushing data through to the data paths. And that has a lot of cascading benefits, some of which we talk about in the paper. Although I said that these are scratch pads, in reality, we use a much more sophisticated storage idiom called buffets, which provides both synchronization and storage. And I encourage you to read the buffet paper to figure out learn about all of the advantages that it provides. And lastly, these EDDO architectures have a bunch of hardware widgets for exploiting reuse. For example, they have multicast capabilities, which means when you fetch a piece of data from an expensive storage element, you can multicast it over wires or networks to multiple receivers, which is far more efficient than reaccessing the same buffer multiple times. You also have the ability to forward data between units, and you also have this interesting ability of performing things like reduction adds over combinational logic in wires or over the network, which is also more efficient than doing it temporarily by accessing the same buffer multiple times. So these are all the benefits, but you also have certain challenges. The biggest challenge, of course, is programming it because there's no single binary. You've got all of these distributed binaries that need to work together to execute the program. And just to give you an example of the scope of the problem, for a CNN layer implemented on one of our EDDO architectures, we have to program 250 different state machines. The next challenge is that reuse optimization is critical. The hardware has reusabilities, but you have to use them. And because of the various ways in which you can map the algorithm, there are various reuse possibilities, and they all have dramatic differences in their energy efficiency profile. So as an example, one of the workloads you're looking at had 480,000 different mappings, and there was an 11x spread in energy efficiency, and only one of the mappings was optimal. So what that means is you really need a mapper or an optimizer. It becomes a critical part of your compilation flow. The third challenge is that there's no single EDD architecture. There are a variety of EDD architectures, and they're constantly evolving. There's a lot of interest in these architectures now. And so really what we need is an abstraction for these architectures that would enable us to build a single flow but target a number of architectures for that. And that's the topic of this of our paper, which is this abstraction, which we call hardware space-time. Before we talk about the abstraction itself, let me try and frame the problem a little bit in terms of our flow. So the flow we have is that of a mapper or optimizer, which takes in a workload and produces an optimized mapping for a given architecture. That mapping then goes through a code generator that we call PolyEDDO, which generates a bunch of decoupled programs that will eventually be mapped onto the hardware units. And then on the back end, you have some architecture-specific configuration generators. Each architecture is going to have some idiosyncrasies, and so you need some architecture-specific steps. There's no avoiding that. But as far as these two steps are concerned, we would like to use the architecture described using our hardware space-time abstraction as an input into these stages. There's a third place where this also serves as an input, which is it so happens that activity counts for data movements can be generated almost as a side effect of this code generation, which can further be fed into analytical microarchitecture and energy models, which can help tell the mapper about the goodness of a particular mapping. In other words, it can serve as a cost model. And that cost model is also going to take the HSD as an input. So this is sort of our overall flow, but today I'm only going to be talking about the abstraction itself and also give a brief overview of the some of the steps in the PolyEDDO code generator. So let's get into it and let's start talking about the abstraction. So the complete abstraction is called HSD. Let's talk about the first part of it, which is called symbolic hardware spacetime. And the way that works is this, look at it with a simple example, which is just an L2 buffer and 4 L1 map instances connected to it. So the symbolic hardware spacetime for this hardware also has 2 levels, and it's a tree. At each of the levels in the tree, we create this spacetime field, right, or the spacetime space that are sort of holes into which we're going to eventually schedule and place tiles of the workload. Now, in this example, because I have 4 L1s, I've got 4 space coordinates. I just picked a random number for my time coordinates. It's 3 in this example, but it's actually, in reality, it's derived from the workload mapping. But 3 will suffice for this. Now, the way to think about this is each of these time steps is a slot for the L2 to potentially deliver a new tile of data to the L1. And so across these time steps, the tile resident of the L1 can change. However, as we go through these time steps, the tile resident of the L2 is not changing, right? So all of these tiles are subsets of the tile resident of the L2. And that's why time does not move for L2 in this example. So that's why there's exactly 1 space coordinate and exactly 1 time coordinate for the L2. And you can see that in this more formal specification of the spacetime. You've got S2T2, S1T1. This is stuck at 0, 0, and then you've got these constraints that describe this plane for L1. Moving on to a more complex example, we add another level to this hierarchy, and the SHST for that is basically a fractal composition of what you saw before. We now have 3 levels, an L3 level, an L2 level, which has now become a plane. You've got 2 space coordinates corresponding to the 2 buffers here, and 2 time coordinates, which is another random value that I picked out. And underneath each of these spacetime coordinates, you've got a spacetime plane for the L1s. Okay, and the formal specification is very similar to that. Now your L3 is stuck at 0, 0, but your L2 has these constraints that describe the shape of these planes. one more thing I want to point out over here is that if I want to address one of these bubbles, I have to trace a path from the root of the tree and find out what its address is. So here's an example. If I want to talk about this blue bubble, I have to start from the root, which is trivially 0, 0, then walk over to the address of this bubble, which happens to be 1, 0, if 0, 0 is the bottom left. And then 2, 1 is the local address within this plane, right? And so concatenating all of these together allows me to identify a very specific bubble. This will become useful very soon. Okay, so that was the SHST. It's a fairly useful abstraction, but it breaks down very quickly. And one of the ways in which it breaks down is if I have this thing called partition buffers, which is a very common idiom in many modern accelerators. The idea being that you hard partition a set of buffers for efficiency to place different tensors into. And it breaks down, it breaks our SHST abstraction because it's not strictly hierarchical anymore. So the way we solve that is by actually creating another level of abstraction. And so the SHST for this hardware is actually identical to the SHST for the non-partitioned architecture we were looking at before. If you remember this picture, it's exactly what was there on the previous slide, and the same thing is there for this symbolic representation. However, we now create this thing called a PHST. So notice that I created a time axis for the physical units on this slide. And then the sort of the space-time of each of these hardware units is represented by the PHST, except it's not a tree anymore, it's just a flat space. So DRAM is still 0, 0, but your buffers A, B, and Z now have a set of space-time coordinates, but there's no tree-like relationship. They're all just independent flat spaces. Now, here's where the HST comes in. The HST is a projection of the symbolic SHST onto the physical HST. And so the way to think about that is, if you remember, I was pointing out on the previous slide how to talk about one of these bubbles here. So you take one of these bubbles here, and then you say, okay, if I were to take the symbolic unit and project it onto these, how would I do that? And so here's an example. So if I take 0, 0 and one of these, so that forms my LHS. I project it onto the physical space by sort of using these indexing expressions. And I have a set, one distinct projection for each partition in the hardware space that I want to identify. Okay, so this is the HST, and actually this gives us all of the flexibility that we need to describe a very, very large variety of architectures. So one interesting thing I want to point out over here is that even though we have this, all of these SHST, PHST, HST, in terms of workload mapping, a workload actually always targets the symbolic SHST, right? And that makes it really intuitive to describe workloads because it's the SHST is a nice hierarchical tree-like structure. Okay, so this was one example. In the paper, you'll see an even more complicated example, which is which uses some pretty crazy relationships in the interconnection network. You've got all these diagonal lines, which are intended to capture convolutional reuse, actually sliding window convolutional reuse. So one of the things I want to observe is just think about how different this architecture is from CPUs and GPUs, right? So we really are talking about a different class of architectures. So that was the abstraction. So now let's briefly talk about how the PolyEDDO flow uses that abstraction. So the flow takes as input an architecture description in HST form, a workload description, and a mapping, and goes through these steps. Let's talk about what this mapping is. I'm going to use the example of a perfectly nested affine loop. The PolyEDDO infrastructure is capable of more than that, but we're focusing on this for now. So we start with the iteration space of the workload, and we basically tile it into as many levels as there are levels in the SHST. So in the example I'm going to show, there are 3 levels in the SHST. So I'm going to do one level of tiling and then another level of tiling. You get 3 total levels. And then I project each of these levels into the corresponding level on the SHST. So for example, I deliberately chose 4 tiles here to correspond to the 4 space-time slots in my SHST. And so what that means is this projection can be any affine function that projects these tile IDs, these distinct tiles onto these space-time slots. And the same thing is true over here at the L1 level as well. I've got these 12 boxes over here, and I can use any affine projection to project them onto these 12 space-time holes. And the choice of projection, of course, is going to dramatically change the order in which data moves about and all of the reuse opportunities available on the hardware. So that's how we express mappings today. And starting from those mappings, we derive this thing that we call a tiling relation or a T relation. And the idea behind the tiling relation is, given a hierarchical coordinate for one of these SHST bubbles, the T relation tells us the set of tensor coordinates that must be present at that space-time bubble in order to honor the mapping. So the interesting thing about the T relation, though, is that it tells you what tiles of data must be present at that point in space-time, but it does not tell you how that data got there. Okay, and how that data got there is something that we will be deriving shortly. The next step, the next transformation step, is this very critical step that we call decoupling. And this is where we start moving things towards EDDO land. So taking a step back, what do we have so far? We've got our SHST representation of the hardware. We've got these T relations which come from the mapping that tell us how these SHSTs relate to tiles of data. And then we've got the HST, which tells us how the SHST relates to physical hardware units. So we take all of this together, apply a set of transforms, and then we decouple this into these parent-child transfer relations. So what are transfer relations? They tell us for every physical parent unit and every physical child unit, what tiles of data, or more precisely, what tensor coordinates need to move at these points in space and time in order to honor the mapping. And so so a couple of observations. We're in pure PHST land now. We've completely discarded the SHST. We don't need that anymore. We've also discarded the hierarchy. We don't have any hierarchy here. It's just pairwise parent-child relationships, and that's what makes it decoupled. And the way that these X relations look like is you've got some source, some destination, and then the tensors that need to move between that source and the destination at a given set of space and time coordinates. So these are what we call data transfer relations or X relations. That's the result of decoupling. The next step is reuse analysis. So now that we have pieces of data that need to move, we can actually figure out that some pieces of data actually never really needed to move. So for example, if this coordinate here had a piece of data at time t-1, and it also has a piece of data at time t, then it can reason that it actually didn't need to bring it in from its parent. It could have reused it because it was already available. So that's an example of local temporal reuse. It could also have gotten that data from a peer that had it at t-1. So in this example, this blue bubble is able to get data from the red, green, or purple bubbles from a previous time step. And that's what we call a fill from peer. And again, this is one of the very important capabilities of EDDO architectures. Filling something from the parent is, of course, the base case. You have to get something from the parent at the beginning of time. Nobody else has it. However, this gets really interesting when we consider the possibility of multiple space coordinates at the same time coordinate needing the same piece of data from the parent, in which case the parent can do a multicast, which is extremely efficient. And we can detect all of these by doing analysis on the data transfer or X relations. Okay, so it turns out that oftentimes you have multiple places from which you can get the data. And what that means is you basically have an optimization problem now. Do you get it from your parent, you get it from peer A, from peer B, etc. There are a variety of ways to solve this. We're leaning towards a heuristic solution, although it is possible to actually expose these choices to the optimizer or mapper running around PolyEDDO. Okay, so I described these three stages right now. There are a couple more stages of transformation. They're briefly described in the paper. I encourage you to go and read it. So the output of all of this is a set of these decoupled programs. So if you look at one of these blocks, here's a program to read weights from DRAM into the row buffer. Here's a program to read weights from row buffer to the row broadcaster. Here's a program to compute the multiply operation. So these are all distributed programs. They're all firing concurrently, talking to each other in order to execute the workload. So as of today, we have the ability to actually build this code as is with against an EDDO emulator that configures itself based off of the PHSD. But in future, we would like to target a real code generation flow for an actual hardware. Okay, so that brings me to the end of this talk. I presented an abstraction for EDDO architectures called HSD, as well as a work in progress flow, analysis and code generation flow based on that abstraction. There's a lot of future work we would like to do. We need to complete the PolyEDDO implementation, and we would like to describe it to the community. There's the whole issue of what the outer optimizer or mapper is. We can try to plug in with existing mappers or write one of our own. And then we would like to expand this, the scope of workloads and mappings that we support. And a longer term objective is to try and analyze compressed sparse workloads and architectures. Thank you very much, and I'll take some questions.
So there are a couple of questions on the chat. Are all transfers pointwise, like send and receive, or can be there some collective transfer?
Right. So let me bring up my slides. Yeah. So at the stage of analysis where we're doing these X relations, they're pointwise, right? We're reasoning about individual coordinates at a time. But as you saw, I don't know if you saw the reuse analysis slide, broadcast inference is something that we explicitly look for. And so in terms of block transfers, yeah, so it's not something that we're actually analyzing today, but it's definitely something that you can do, which is you detect that a set of coordinates are contiguous in some space, and then if there's a hardware primitive that allows you to transfer that contiguous block in an optimal way, then you can take advantage of that.
Yeah, any other questions? So there was also a comment telling that in some slide there was only 2 levels, not 3.
I think we were interacting while the recording was going on.
Oh, okay. Okay. So I just have one more question. So the T mapping, I'm not sure if I'm recollecting the name correctly, but the one which maps one, like what is the exact data that you require? Is that specified? How is it actually specified?
Yeah, so let me bring up this slide. Can you see my slide?
Yes.
Yeah. So this is the slide you're asking about, right? So given a point in space-time, what's the set of coordinates that need to be mapped there? So it's derived from the mapping, and so this is my previous slide, which describes a user-specified mapping, and so the user says, hey, I've got a hardware which is represented by this 3-level SHSD. So I've got to find a way to partition and chop up this workload into tiles and map it onto the hardware. And that mapping is described by, okay, what are the sizes of these tiles that I chose, and what are the projections that I use to project these onto space-time. So the T relation is almost an inverse of this projection, right? So the user basically, you go from here to here, and the T is kind of an inverse.
Yeah, projection can be viewed like an affine schedule for that particular level.
Yeah, I think I understand. So basically you partition the iteration space and do the inverse mapping to find the access to data, right?
Right.
We started exploring the polyhedral model in sort of analyzing and doing the code generation for EDDO architectures. If you don't have questions, even if you have some feedback, that would be very helpful to us. If you have any feedback also, so please talk in this forum.
And once again, the gather space is available until 8 p.m. Brussels time tonight, so don't hesitate to use it.
Yeah, maybe we could use the other channel for discussion.
Okay. Sounds great.
So let's, is there any other question? Okay, so then I would like to thank the speaker. So yeah, I think I will hand over the session to Albert for conclusions.
Okay, I'm not sure I have a conclusion, but I have a slide at least. Let me wait a second. Okay, so that's not the break. This is the right one. So I'd like to thank you again for participating to the workshop. So I think this is not an ideal situation, but we have made the best of the technical means of communication that we have been provided with. So thanks everyone for asking lots of questions, engaging into discussions, chatting on the and networking on the Gather space. So please continue doing so. Just imagine we are still just a corridor away of more discussions, and there is a coffee break next door. And especially those who still have time, please try to do that. I'd like to thank Arvind again for doing most of the work for the paper, for the program committee itself, because I was conflicting with half of the papers, so that was not practical. Again, thank you everyone for joining and submitting papers. And we will come back with news about impact next year. Hopefully it will be in person. I don't think HiPEAC has decided yet where the conference will be, what the format it will take.
I thought Kuhn mentioned that they would take place in Istanbul. Sorry, Budapest.
Oh, Budapest. Okay, yeah, Istanbul would be a big challenge. So yeah, it would. I mean, actually, we did plan to have HiPEAC conference in Istanbul a long time back, but that didn't happen. Hopefully, at some point. Yeah, so Budapest was the original plan, so that would be logical. So hope to see you all over there. And if you have questions, please, or feedback, especially, please send us an email. Thank you, everyone, again.
Yeah, let's all thank Albert also for his major contribution. He has spent sleepless nights to organize everything. I mean, yeah.
Thank you, Arvind.
Thanks, everyone.
See you in Gather.